Okay, so we shall commence, and whoever joins is welcome. So let me officially now say welcome to everyone who is now in this WebEx chat, to our attendees and to the group of panelists. Thank you all for your commitment to the panelists and for the time to the attendees on a Friday afternoon. I hope to meaningful talk.
We cannot hear you anymore.
Panelists. Let me share my screen. For a second. Okay. What I would like to say as a beginning is that I believe you already see my slides, right? Is that when we were discussing with the people who are organizing the biotech atelier, the possibility of introducing water, we were brainstorming various topics and various concepts that we can spend a couple of hours reflecting on. And I just wanted to put some of these on a single slide as text boxes. And many, not all of these, we'll try to cover in our panel today. It's the biotech atelier is in its third year, but water as a specific topic is this is the first panel that addresses the topic, and we were thinking of topics such as water quality, water testing and related analytical activities, particularly microbiological and genetic testing, real-time PCR and related methods and approaches. Then we somehow naturally move towards everything that is to be detected from the sewers, and luckily this is a topic that we will cover in a good level of detail today. The detection of viruses, bacteria, and other substances. We initially wanted to spend a fraction of our panel on water as health. Unfortunately, this is something that we will not cover, but we will deeply cover the third topic that we announced on the website: water stress, water droughts, and the impact of drought on plants, animals, people, etc. Of course, it was inevitable that the topic of water quality and detecting viruses and bacteria, it's inevitable that this topic crosses with the COVID-19 topic, which I think is good because it, not because there is COVID-19, but because the significance of water utilities, particularly in the area of early warnings, early detection of the availability of the virus in sewer water is a topic that is gaining recognition. So these are the kind of topics that we were discussing among ourselves, the panelists, and with the core organizers of the Biotech Atelier. And even if we don't manage to cover all of these today, I hope that will be a good beginning for future events to come. I'm sure everyone who is now attending our panel has seen who is joining as a panelist, who is expected to be speaking in the coming minutes. I'll just say a couple of sentences for each and every one of you, and then when you start your presentations, please also properly introduce yourself. Teodora Todorova, who is actually sitting next to me here in the same room in Sofia, is a colleague of mine years ago in Sofia Water Utility, and she's an expert and a manager in the water sector, so deep understanding of the way water utilities approach the topic. She'll be talking about water testing methods, regulations, what is expected and what not from water utility laboratories. She will speak a bit more about methods, about microbiological and genetic testing, its application, why utilities are doing, why not, what can be done, etc. I think then it will be somehow natural that the topic would be further developed from Norbert Kreuzinger, who would, as a assistant professor in the Technical University of Wien and deeply involved in water quality and resources management. I went through your slides, Norbert, and I was very happy to see your key slogan that wastewater is becoming a mirror of our society. So that's, I believe, the slogan of your presentation. And then Norbert will go deeply into epidemiological topics, etc. And towards the end of his presentation, he would move more on the water reuse topic. After him, I would give the floor to Professor Atanassov, distinguished Bulgarian scientist in the area of genetics, agronomy, and a number of related scientific fields. I've been knowing Professor Atanassov for quite some years now, and the way I got to know him was through the Joint Genomic Center in Bulgaria. From the various topics that he's capable of covering, I'm particularly happy that he will make a wider introduction to the water needs and water availabilities and the water stress that is related to that. And then in more depth, he will go into what this means for agriculture, for plant breeding, and some quite interesting topics such as epigenetics, plant breeding methods, etc. And then we will give the floor to Dr. Josef Lahnsteiner in what I believe would be a very straightforward introduction to what has been done globally as water reuse installation, treatment plants, case studies. Very practical, I would say, presentation on from a practitioner's perspective, because he represents one of the leading companies, WABAG Group, with lots of experience in designing, construction, probably operating treatment plants, etc. But I think that would be a natural way from the analytical part from Teodora through the that way of bridging the engineering and life sciences approach from Norbert. Professor Atanassov will then tell us a bit more about drought and its impact on plants, and then Joseph will speak more about the practical applications of water reuse. Just a couple of words about logistics. I think in the last 6-7 months, we're all getting used to these events. I'm still find it a bit tricky with these online panels, but the overall event is going to take as long as it takes. The panelists, please do not be constrained to what I initially indicated to you. Feel free to have 15 minutes plus minus. If you go above 20, I will stop you or request you to shorten it down, but take your time because the topics require certain depth. So I believe that we will have about 1 hour plus minus of presentations, and then I will be happy to moderate a discussion. So for the attendees, please send over whatever questions you may have or comments in the chat function. We will be receiving this. I will not be filtering them. I mean, I'll just try to raise them to whoever is the relevant person to answer them. Please make sure that you direct the questions. I mean, make it clear in your notes who you believe is best qualified to answer your question. Simple enough. And I just want to confirm, because a number of people contacted me before the event and asked us whether the panel will be recorded. Short answer is yes, it will be recorded. And everyone who has registered for that panel will receive by email a link to the recording. So there will be recording even for ourselves, but for sure everyone can approach that. So let me stop here and stop sharing my screen and pass the floor to Teodora with her introduction on water quality, testing, analytics, etc. Thank you all. Looking forward to what Teodora is going to tell us.
Good afternoon, everybody. I'm happy to be part of this panel and have the chance to discuss and share with you my point of view regarding the topic of biotechnologies and the link between water and genetics. Well, thinking about the event and when we started the discussion with Rado about it, I was thinking to myself that in fact we are a good mixture of water, genetics, and some other stuff. So we ourselves are bringing the link between the two topics. But having the perspective of water utilities from my past experience, I would say that it is inevitable that we discuss this topic, especially with the current events and situation with COVID-19, which is bringing some new challenges to all the society. So when we speak about water and genetics, we could not avoid the topic of testing. And yes, all the water utilities, all the water operators, and not only, but different stakeholders are doing such testing. So speaking about it, I would like to say and to put a stress on the fact that utilities, but also health authorities, in fact, all the institutions which are part of this testing ecosystem, I would call it, are doing whatever the regulations are requiring. But for me, the question is this really enough? Are we safe? Is everything secure? Having in mind that okay, evolution is changing the life around us and is changing ourselves as well every day. Do we know everything that is existing and living in the water? Do we test for everything that is dangerous for the human health? Because inevitably the quality of drinking water, for example, we all know that how much it is linked with human health and what risks can emerge there. The fact is that, for example, utilities, they're testing for what is written in the water regulations. And this is not only valid for Bulgaria, this is valid for the whole European Union. And there we can get into a vicious circle trying to understand which is first. Of course, the local regulations are based on the European directive. So the health authorities and utility operators, they would say, okay, we are testing what is written in the local regulation, and it is compliant with the European directive. However, the European directive is saying that, okay, the local authorities can define further parameters of what is written in the European directive. So coming to the point of what is the list of parameters today in terms of microbiological and genetic testing. In fact, what is required are only a few parameters for drinking water and close to no microbiological parameters when we come to the testing of wastewater that is discharged from sewer systems to rivers or after wastewater treatment plants. So having all this said, I would say that it is what the utility operators are doing is doing their routine job as per the list defined by the regulations, and they're testing for E. coli, for enterococci, for salmonella, for cryptosporidium in certain countries, but not in Bulgaria. And in fact, there are not any requirements to test viruses. So this is bringing a question mark to how safe are we today, knowing that, okay, there are some new emerging pollutants in the sphere of microbiology and viruses, not testing for what is in fact in the treated water, how likely it is that this can cause an issue for the end consumers. The focus today is on chemical pollutants, including emergent, such as microplastics, which was a really posh topic a few years ago, residues of pharma products, drugs, etc. Of course, microbiological testing of water is mandatory, but we shouldn't forget that maybe we don't know everything today. So, what is the challenge when we speak about water and wastewater testing in terms of microbiology and viruses? Traditional testing methods give very good and very reliable results. I can say this having my experience like years ago into managing laboratories of a water operator. So the classical microbiological methods are really, really reliable. The thing is that unfortunately they have quite a lot of limitations or requirements in terms of time. It takes between 24 and 84 hours to produce a result after first gaining the sample. So this time frame can be very dramatic in case of emergencies. If we are doing a routine testing and we know there is no pollution in the water source and we're just reconfirming that the water is safe for drinking, it is great. But if we have to deal with an emergency situation, I would say that this would put on the edge any water operator, any health inspection anywhere in the world. So those classical methods which are using filtration of samples, placing them on media, on a petri dish, then growing whatever is in the water, hopefully nothing, and then confirming that we have found or didn't found anything. These classical methods cannot really, in my opinion, cover the current demands when it comes to water testing. We should be having, the water operators should be having something which is quite more fast in terms of time, and also methods which are giving broader view on the pollutants. Because with the ISO methods listed in the European Directive or recommended by the European Directive, the ISO methods for microbiological testing listed in the local regulations, we are testing for only few microbiological pollutants. Unfortunately, those methods are showing, for example, there is E. coli, and if the colony is with a certain color, with a certain size and shape, etc., then you can confirm that this is E. coli. But still, you can be having on the petri dish something growing, which is maybe similar, but maybe not. And then you need to do a confirmation test, so you have another 48 hours in the best case scenario to confirm that you have found some life form which is not E. coli, but maybe something else. And this is where the limit comes unfortunately, for the most of the utility operators, because they cannot go further into the diagnostics. They can say there is a microbiological pollution of this water sample. We know that it is not E. coli, okay, so we can be safe, but maybe not, but we don't know what is it. And if we have a virus in the water sample, then no chance that we can register it by those methods, and it will stay unknown. However, it could reach the consumer and generate some issues. So testing bacteria is going to a certain size of those pollutants, but not going down to the size of the viruses. The solution, in my view, is to introduce PCR testing for routine microbiological analysis. Why? Because first, we should, as a society, move into the direction of testing everything that we could identify, or at least try to enlarge gradually the scope of the pollutants that we are testing for, with the thought of first preventing human health, and second, preventing what is discharged from, for example, wastewater treatment plants to the rivers, seas, whatever the place is. Also, PCR testing could be, in my view, very useful for the so-called water safety plans. Those safety plans were introduced by utility operators in the recent years, and as part of those water safety plans, the utility operators are required to do kind of a research of all the elements which could be contributing to pollution of the water sources, but also the efficiency of drinking water treatment, the efficiency of wastewater treatment, the chances that some pollutants might get into the supply systems and reach the final consumers. So having a good PCR testing machine equipped with the sufficient number of options to test and qualified personnel would only benefit the water operators and finally the end consumer. But there is a certain limitation, as for any other topic, I guess. Utility operators, as we all know, are challenged to invest, and their main demand is to invest into infrastructure. And their top priority, unfortunately, is to invest in infrastructure. There is very limited budgets which usually remain available for anything else. And when it comes to research activities, this is not something which is part of the core activities of the utility operator. So very few would be able, even if they would like to put money into purchasing equipment and developing testing methods to investigate for something which is not required by the regulations. And this is, for me, really a big challenge for the utility operators to overcome, even if they have the best will in the world to test for additional pollutants, to enrich their water safety plans, etc., etc. So why would it be worth to make effort and invest in PCR equipment and training of laboratory personnel? Well, I have listed here a few sentences coming from a document which was produced by the European Commission related to methods of testing of microbiology in water. And I would say that, yeah, I agree with all of this. Microbiological water contaminants represent acute health risk in drinking water. Yeah, that's true. We all know it, etc., etc. There are limiting factors related to the classical current methods of microbiological testing. Yes, this is true. Current methods can consider the viable form of pathogens in the water samples that are tested. Yes, this is true as well. And it is also true that, okay, we do some disinfection of drinking water, for example. The sample shows negative for E. coli, but if finally there is residues of the DNA in the water, there are some researches which show that those bacteria can regrow, can revive, and get back to life into the water supply system, especially when we're speaking about very large water supply systems, especially when the velocity of water is slowing down depending on the consumption, and so on and so on. So the water maturing in the water network, there is a risk that it will not be so safe anymore, and this is why utility operators are pushed to do secondary disinfection in different points of the supply network to make sure that, yes, finally the water will stay safe from getting between the drinking water treatment plant until it reaches the tap of the end consumer. And last but not least, the quantitative PCR methods have very high specificity and sensitivity, and they require fairly short time for detection. Yeah, this is true. But moreover, we need to be prepared to act, protect the end consumer of drinking water and the ecosystems. And we should be able, in my view, to identify in advance the treatment options for alternative chemicals, so that the water operators are well prepared in advance before any emergency situation appears, and get ready to act if such comes. Well, it's very famous these days to speak about the new normal. we know that there is an overall uncertainty about the topic of COVID-19. However, it seems that there is no big risk for the drinking water, and there is no huge tension against consumers of drinking water. I was thinking of another element here. It becomes popular for not really for utility operators, but for different businesses to state that their sites or their services are somehow COVID-free. And having this said, I was thinking that maybe it's worth to raise the topic of developing some standard sets of tests to confirm a site or a public accessible closed space is really COVID-free. And of course, part of this testing protocol, in my view, should be linked with the water, including tap water and wastewater, but also surfaces, indoor air, etc. Unfortunately, we have to consider that maybe we don't know how the future will look in 5 years, in 10 years, and what it will bring. However, I believe that we are still in control. We are in control to still research, to test, to inform all these interested stakeholders, to prevent, and if anything happens, then of course to get into the part of the cycle of investigation, correction, and we should start all over again. And without doing this cycle, starting with the research and ending with the corrective actions and further research, we will not be able to manage precisely all the risks that are linked with water and the genetics into it. And this will be valid, in my view, as long as the planet will keep evolving, as long as the genetics of the living world will keep evolving. Thank you.
Thank you, Teddy. Let's have a bit of microphone here. Thank you, Teddy. I think that was a good introduction from the perspective of the water testing expertise, the perspective of the water laboratories in water utilities. Now, in order to start making the bridge between the engineering and the life science areas, I would like to give the ball to Norbert. So, please.
So, well, hello, everybody. Pleasure for me trying to give you a bit of an overview about some of the core topics of that event. So my name is Norbert Kreuzinger. I'm with the Vienna University of Technology and here within the Institute for Water Quality and Resource Management. And I'm from a position more or less try to bridge the engineering point of views with the environmental and natural scientific points of view. So I'm a bit between both worlds, trying to understand the demands on the one hand and the possibilities on the other hand. So before I start, because this is already what was mentioned and what is, I think, necessary for the core understanding that we consider wastewater as a mirror of our society. And this is something that actually in certain areas was clear since long time, but it's not really what the society how the society looks at wastewater. So for the society, usually wastewater is just some pollution that you have to get rid of about in order to protect the environment. But when you have a bit more diverse look, then you see, and when you look at the different water consumption pathways in our urban water cycle, domestic agriculture or industrial use, you see that it's not only drinking water we need for physiological needs, but especially in the domestic side, most of the water is just used and needed for the transport of pollution. So when we spill our toilets, when we take a shower, it's more or less getting rid of pollution, and for this we need actually most of the water at home. And then, of of course, we have agricultural use, industrial use, and so on. And all that, what? How to shift now? All that water more or less collects pollution that occurs within the use of the water. And on the one hand, of course, we have substances that are directly excreted by the human body. For example, when you take some pills and pharmaceuticals, they are not degraded. Most of them are not degraded in the human body, so they are excreted. But it's not only pharmaceutical in our feces, but you have commensalic and pathogenic microorganisms of various species. The same is then for cleaning. So even when you take a shower, then you take some gel or some soap or whatever, and then you spill it from your body, and everything lands up in the sewer system. And of course, in the personal, so when we use products, it could occur that some of the products that are embedded in or some substances that are embedded in the products are released or even leaching from the products. And one example are the perfluorated octone acids that before that nowadays are actually you will find everywhere. So when you want to summarize, we have quite a bunch of organic trace pollutants in our wastewater. We have microplastics, we have engineered nanoparticles, for example, from toothpaste or other applications. And of course, we have antibiotic resistant bacteria. And I will come back to those topics later on. So when we look at this general topic, what we, in regard to the wastewater as mirror of our society, we can distinguish mainly two aspects. One is the biological side and one is the chemical side. And I just want to start with the genetical side. And there was already a very nice introduction, some methods and the advantages, disadvantages of all the methods that you can apply. And nowadays, of course, as you can imagine, we have, based on the SARS virus, a new look at the whole topic as wastewater from the genetic point of view. And one aspect that we link up, or a term that we link up with that, is wastewater epidemiology. So basically, the basic idea or principle behind that approach is that we release, as already mentioned, chemicals, substances, microorganisms via the feces or even the urine, and that is collected in the wastewater. And when you now consider the inflow of a wastewater treatment plant, then of course this wastewater that arrives at the treatment plant is collecting all this waste, all this feces, all these excretions from all population that is connected to that. So you're really getting a holistic, anonymous mirror of the whole population that is connected to the treatment plant, and that gives you some advantages that other modes or other ways of trying to get an overview about the society do not allow. So basically, when you analyze the wastewater, then you really get a very broad information on the connected population. And this application actually is not really new and not now recently implemented with the SARS virus, but for example, used already since years for the monitoring of lead drugs. So that means you can, for example, measure the cocaine or the degradation products from the cocaine in the inflow of waste to the treatment plant. You can multiply it with the water that you have per day there, so you get a total load, and the total load you can divide by a drug dosage per consumption, and then you get an idea about how many people are consuming that specific drug. And this gives you really very reliable information on the drug consumption in your society. But even parasites or helminths are investigated even where you don't have wastewater treatment plants. So think about peri-urban regions in Africa where you have the wastewater collected in just a surface water system. And of course, you can analyze that system too and get some information about the pandemics or the epidemics in regard to parasites or helminths. And of course, looking at polio, the WHO just announced that polio was extinct from that planet. And how do they know? Why do they know? know, because they are doing wastewater monitoring worldwide on a broad scale. And when you don't find the virus for a long time in the wastewater, then you can be sure that there really is no virus in the population. And of course, nowadays we use that approach for the SARS virus too. And so what's the basic idea behind it? You can do chemical analysis, as mentioned. You can do even culture-dependent methods. You can do immunological methods, or you can use molecular genetical tools that already were introduced. They are very powerful, but you have to be aware that even those methods have their limitations, that they have the pros and cons, and you always have to raise the question first, what do you want to know, and then select out of the toolbox which methods would provide you with sufficient and reliable information in regard to answering your questions. So there are a lot of questions where you can apply molecular genetical tools. And basically the idea is when you have a person in your population that's got infected with the virus, you're collecting the feces. Also the feces are released in the toilet, in the sewer system, and then you have daily composite sample, for example, of the inflow of the wastewater treatment plant, and then you can analyze that signal and you get then the corresponding result. So, and linked up with the SARS virus, there were very high expectations in the beginning to use it as an early warning system to get some information on the unknown or unreported cases. But what could be very important for pandemic management, even as a de-warning system. So let's imagine you don't find the virus anymore in the sewer system for 2 weeks, then you can be quite sure that there is no one spreading the virus, and you could maybe think about releasing certain measures. When you go into detail, then the problems and the questions arise. So this is just in the middle of the picture, you see the same picture as in the previous slide, with the population releasing feces sampling, then the sample preparation, processing, analytics with qPCR, and then you get a signal. And when you have a closer look, then there are a whole bunch of different points where you have really, really high methodological challenges. I don't want to go into detail on all of them. But there is really crucial crucial aspects that you have to consider in order to get really reliable results. Just one hint here on the left side. So we don't even know nowadays, and the answer maybe never will show up, how much virus particles is a person discharging via the feces. So we know people that are infected, they release virus particles via the stool, and we can detect that in the wastewater. But when we detect a certain number, let's say 100, then how many people are spreading or releasing those 100 particles? Is it one person with a 150 kilogram person that is releasing everything because he's in the high peak phase of his symptom phase, or is this 10 smaller girls with a body weight of maybe 50 kilos that are somewhere in the last phase of their excretion? So we don't know that. So for that reason, it's really close to impossible to recalculate the amount of infected people out of the signal in the wastewater. We don't know how much of the virus we lose in the sewer system due to adsorption to the biofilm, due to some degradation, due to temperature losses, and so on and so on. So there is really a huge potential of methodological problems that nowadays are only recognized, and where people think about how to copy those problems. And the pure methodological aspect here on the top right is maybe the easiest part out of it, that you may be able to solve to some extent, but the part of the release into the sewer is really something that is hardly where you hardly can really get sufficient information to calibrate or for a meaningful calibration of models. So this is just to say that there are high expectations, but we cannot really be sure today if we really can solve that expectations. And of course, there's another issue. Someone said never do research in parallel to a pandemic situation, because everyone is expecting results, but in science you need time to really have replicable and meaningful results to answer the questions. So nevertheless, we in Austria too did something that quite a lot of countries did. We do some wastewater monitoring. So we have this Corona A research project. Further information you can find at the homepage. We are monitoring roughly 20-25 treatment plants on a regular base, some of them on daily base, some of them 3 times a week, some of them once a week, some of them every 2 weeks, and we have additional treatment plants and we monitor where we have specific research questions, and we hope that we can answer them sampling those plants. And on the right side, you have the result for one city where we sample twice a week. And the black line is actually the official cases that are reported. So with the high phase in beginning of April. And the brownish dots are the signal that we get from the wastewater. And you see that we can measure, or that we can follow the prevalence curve quite nicely. So we lost the signal in June because the intensity was too low. But then we got the signal again roughly 1 week before July, so end of June. And this still was a situation where the prevalence case, the official cases were not increasing. So they only increased 10 days later on. And we observed this for 2 cities that we really can obtain a signal about 7 days, 10 days before we observe an increase in the official prevalence numbers. Another interesting situation occurred with mid of August. So despite the fact that the prevalence data is increasing and increasing and increasing, the signal in the wastewater stays more or less stable. And we were discussing this with virologists and epidemiologists, and the hypothesis now is that despite the fact that we have more people infected, the severeness of the illness may be not that as severe as in the beginning. So the people release less amount of virus, and the amount of virus in the wastewater stays constant. Okay, this brings me to the second important topic in regards to antibiotic resistance. And this is actually something that I really consider is very important, much more important as microplastics, several orders of magnitude more important than microplastic, because it really directly affects our society and our hospitalization practices. And the problem we have here with wastewater treatment plants and antibiotic resistance is that we have a very close contact between clinical relevant bacteria and environmental bacteria, meaning that the resistant genes can be transferred from the clinical to the environmental sample due to the close contact. And we we have no other compartment where we have such a close contact with that high amount of bacteria. So despite the probability of a horizontal gene transfer is very, very low because of this high amount of bacteria we have in wastewater treatment plants. We have several cases per day where we really can observe a horizontal gene transfer. We still don't know about what it means and what's the significance, but we can prove that this horizontal gene transfer between clinical bacteria and environmental bacteria occurs, and we are building up on a corresponding gene pool in the environment. There are very nice studies that look at antibiotic resistance in wastewater. This is just one example from the Joint Danube survey, where within the Danube catchment, 12 wastewater treatment plants were analyzed, and the abundance of various antibiotic genes were measured. So the color more or less indicating the amount of the genes. And you see that certain genes are very, very frequent, like the SAL1, the sulfamethoxazole resistance, and others, for example, the vancomycin B, is not really was not found in a single of the treatment plants. And this is especially interesting because when you compare those results where we have no carbapenem resistance and no vancomycin B resistance with investigations from hospitals, then you see that in the hospitals, looking at the black KPC. This is the second bar, and looking at vancomycin B. So we have it in hospital water, but we don't have it in the municipal wastewater. And this is not just one observation. This is proven actually by the investigations over the whole catchment within the Danube too. That brings us, of course, to the question how to get rid of the resistances. And what you can do, you can on the one hand remove the bacteria, but it's not only the bacteria, it's the free genes too that you would have to consider. And it's depending on the cutoff of your membranes, for example, how much of the genes you can remove. So when you take pure DNA and try to remove the DNA with membranes of various cutoff sizes here on that axis, you see that when you use microfiltration, you remove not a single gene, so it's more or less permeable for the DNA. And only when you go towards a closer ultrafiltration or even nanofiltration reverse osmosis, you really can remove most of the genes. But it's not that easy, as you can imagine. In science and technology, nothing is easy. Even the charging of the membranes are very significant. So the neutral membranes give you a high removal compared to the negatively charged ions. And this is, of course, important for the operators, especially when it comes for drinking water, to choose the correct membranes for their reverse osmosis or nanofiltration technology. And you can use that technology even for the evaluation of technologies in a treatment train. As here an example for a direct potable reuse scheme, where you have treated wastewater and you produce really then high quality drinking water out of this wastewater. You can follow now the removal of the resistance through the whole treatment chain, and you figure out that even when you have very high abundance, 10 power 6, 7 in the inflow, at the final effluent at 0.9, you are not able to detect anything, and the detection limit here is about 1 copy in per liter. So this is really you have to take a lot of sample, and in order to make sure that, for example, 10 liters of sample, you have to concentrate and then measure whether you're able to find something, a signal or not. And all these methods more or less are really based on molecular biological methods that nowadays get more and more attention in the engineering on the engineering side. So this was one aspect, and the second quick one is water and drought in regard to reuse, and here the term of the contaminants of emerging concern and how to derive quality criteria, how this fits together. The problem we have that when we look at our society over the last decades or years, that the amount of chemicals we use on daily basis in our society, at home, in industry, everywhere in our products is tremendously increasing. And this is just a picture from the number of substances that are registered in the CAS database. And of course, not all of them are really relevant for the environment or for the water, but it gives you a very impressive overview about how our environment, how our society changed, comparing the year 2000, where we had roughly around 20 million substances registered in the CAS database, and now we are around 150 millions. And this within the last years, and already that was mentioned too. Is our regulation really fit for purpose? Can we tackle the existence or the potential hazard resulting from all those chemicals that we don't consider in detail? So we have a problem, and we have to think about how could we tackle with that changing situation with all the different chemicals we use as solvents, as personal care product, as surfactants, flame retardants, pesticides, and so on and so on. So it's really an endless number, and this is just the original compound. So when you have degradation products, then this whole bunch of substances even get more and more in regard or from the chemical point of view. There was a very nice study already some years ago, 2012, where a lot of European wastewater treatment plants were analyzed in regard to some of the most prominent and organic chemicals that are frequently found in scientific literature. And in all cases, they found the before, in all cases, or hardly any, all cases, or in almost all cases, they found the benzotriazole, that is a corrosion inhibitor that you use in dishwashers, and so on and so on. So you see that the number of chemicals in most of the treatment plants is extremely high, and until now there is no regulation and no idea how to deal with that. And the revision of the Urban Wastewater Directive may address those aspects in future. When you look at the concentration, then you see that the concentration can tremendously vary between 2 nanograms and 211,000 nanograms, so 0.2 milligrams. Especially the benzotriazole can be very high in concentration. And of course, the question is how to address a potential effect in the effluent with all that chemicals in this chemical cocktail that we have in the effluents. And there are certain approaches that can or that are promising to deal with those chronic, long-term subtle effects. The first one, the most prominent one, is the hormones, so estrogenic activity. So this was something like the first effect that was observed in the environment, and where the first tests were developed that are now more or less market ready and already applied in regard to the estrogenic effects. But there is quite a bunch of other endpoints available that can be used to assess the cocktail activity of a substance, because it's not only one substance that is responsible for this estrogenic effect. You have quite a lot of substances like plastifiers or the natural hormones, the synthetic hormones, phytohormones that all can have the same effect, and you never ever can analyze those substances and the degradation products. So you have to go for a different strategy to assess the overall activity of these chemical cocktails, and that you can do with these effect-based biotests. So when you look at toxicology, usually the ecotoxicology is on that side, where you look at the different trophic levels, bacteria, algae, daphnia, fish, whatever. And for this biological for the effect-based biotests, you're rather looking into specific toxicodynamic aspects within the toxicity pathway, where you can look at is DNA repair triggered, is cell death triggered, is some signal pathways triggered, or is some oxidative stress response triggered. So you have different tests, and when you apply a test battery here, you get quite a good idea about what's if you can expect a problem in your sample or not. I think that the slides will be provided. I added the one or other additional slide just explaining how those effect-based biotests work. And what is now, as a consequence in regards to policy or politics and operator, there was the MODIS project, EU project, where they tested a whole bunch of priority substances and others for the different tests. And what was very interesting, that when you have a problematic substance, for example here, it not only pops up in one of the biotests, it pops up in quite a bunch of biotests. So here, for example, yeah? So it's so that the effect is not only limited maybe to one test, but the problem is even shown on other effects too. So there's some cross acting characteristics of those substances, and that may help to select certain effect-based biotests as a monitoring tool for the future. Well, and this was a broad journey through genetical aspects of wastewater, that this is really a useful approach, all based on that wastewater is a mirror of the society with all the pathogens in there. So this wastewater epidemiology is a very nice tool combined with molecular methods. You really can get a lot of information out of it, despite the fact there are, you have to know the limitations of the methods and all the degrees of freedom in your system. And the same as wastewater as mirror of the society, you have all these organic trace compounds in the wastewater that prevent reuse of water for various topics, and you have really to link up maybe several safety barriers in your treatment train in order to make sure that you remove really all of those contaminants of emerging concern that in order to have safe water for the reuse. And that's my contribution, and I would be happy to answer your questions.
Thank you very much, Norbert. Actually, a couple of questions already came to you, so stay around after we finish with the other presenters so you can address them. As we preliminarily discussed with you, you indeed made that kind of bridge between the engineering and the life science topics. So now we would like to gradually move to the second big topic of our panel today, which is the absence of water, the drought, the water stress, etc. And I will give the floor to Professor Atanassov from the Joint Genomic Center to enter us into the topic. Here you go, Professor Atanassov.
Okay, thank you. So I was pleased to hear the Norbert presentation, to make some small connections with my presentation. So the topic that I'm talking about is important one because it's related to the agriculture, and as far as agriculture is important sources for the food and feed and various other subjects for the humanity. Obviously, water is the base on the development of the agriculture, but it's altogether it's related, and even so agriculture and food is almost the same. But if you look at, for example, in this slide, the population poverty is obviously that the temperature and water, which are related more than half of the planet, it was serious problem of all the civilization, because the migration is obviously the consequences of such limitations. So the waste and the other things have been strongly related, and the previous speaker already have been strongly related to this. So the water availability is, I would like to consider with the future tendency, and it's obviously that clear that 40% annually, 17 countries, which are almost 25% of the population, is already decreased significantly. So altogether, if we make it the demand for the agriculture is going to the 70% of the fresh water important for the development of the agriculture all over the world. So if you collect what looks like the humanity for the 2050, we need to increase 70% of our food, but twice less water, labor, and salt. So as far as the water is our topic for today's discussion, it is already clear, and I have borrow a couple of slides from my colleagues from Italy, Aldo Ferrero from Torino University, and it shows that 97% of the whole water in this planet is in the seawater, and only 2.5% is the fresh water. So from this is 1% is the surface water and 30% groundwater, and the other is from the let's say Arctic planet. So from this point of view, we are really in a serious problem if we, let's say, if we look at that, we have to accomplish the demands of the humanity for food. And you see in this slide that, for example, Europe is the best continent dealing with the water. At 35% is going for the agriculture. And if you look at the South Asia and Africa, it goes up to the 85, 90%. And averagely this is 70%. So why the agriculture is very important in terms of the climatic changes, and particularly for the water. From this slide, one can see that starting from cattle cultivation, it is more than 15,000 liters per unit, and it goes to the potato, which is less, 287. But because the agriculture all the time is blaming that is the main sources, the main subject which requires water, but you can see that one laptop, for example, needs 20,000 liters for its cultivation. Or if you look at the relationship between the population, increasing of the population with the need of water consumption, we see that we will need more water in comparison with the increase of the population. So it's a big question how we can make it efficient agriculture with otherwise twice more with twice less. For example, in order to we, like plant geneticists and breeders, we have to make a buffer for the water, because for it present needs 3,500 cubic kilometers. We need in the 2050 5,500 kilometers cubic kilometers. So what are the options that we have to deal from the economical point of view in order to make a solution? First of all, strategically, we have to live with the genetics and developing crops which are suitable for water availability. Or with other words, if we cannot develop, in parallel, we have to look at for the alternative sources. The agronomic options are starting from the effective weed control, the right time of seeding, harvesting, proper irrigation, all the aspects of the technology, and finishing with the structural and technological options that we can see in this slide, including the dissemination, but also the treating wastewater and starting secondary use. Okay, one of the very important point, and it's even the small country, for example, in Bulgaria, you can see that we differ from region to region. If we like to satisfy the needs, we need to find and to develop a particular variety of different crops, those which are important, for example, for Bulgaria, for the region, for Europe, particular varieties which are adopted for and properly use the water efficient. But as far as the water, particularly is not the only factor which is important for plant breeding efficiency and the agronomical efficiency as a whole, that we have to consider holistically and interdisciplinary how we approach. And in this slide, you can see that among the 6,000 plant species, you'll have a big options, which are big options to select those which can be used like alternative crop. The second big point is the present crops which are important for different regional continent to apply all the time, constantly, efficiently develop new techniques. As far as plant breeding techniques and new plant breeding techniques are considered, it turned out that they are offering very suitable and convenient option to the GMO plants, genetically modified plants, for example, like gene editing and specifically so-called CRISPR-Cas9 technology, which using like agrobacterium transfer gene transfer method is using the naturally developed technology how bacteria fight against the viruses by directing efficiently the respective by RNA directing to the defined surface of the virus, defined region of the virus, RNA or DNA, and cut in the different places and kill the virus. So this technology now is efficiently used with different modifications for almost any crop. More than 60 different crops already are in place, and different characters have been developed in order to deal without basically GMO. Just you cut the defector, you cut or you replace or you interchange the places in order to develop efficient plants which deals with the proper utilization of water, so-called ground water. Of course, here the tendency is very large and big because as far as the sequencing of the most important crops is already in place, it's very easy to develop such a RNA technology which is dealing and going to modulate, to regulate, to change the activity of different genes or alleles which allow the water efficiency control to be here. And here is the options are enormous and they are day after day developing in a very effective way. So, and this term actually turned out that epigenetics is parallel with the new plant breeding technique is offering new models, new options for how to make the plants efficient in the agriculture. So the plant gene regulation actually is already known without changing the DNA sequencing, without not changing the hereditary way. Actually, we are by DNA methylation, histone modification, and especially by regulatory RNAs, nowadays already in the phase when such methods can be developed by using different, for example, plant regulators, which in the proper moment can be utilized and change the physiological situation of the plants, especially in the severe period of water limitation. And here is a moment when the microbiome is coming and entering seriously in every field of the plant, animal, human development, because it turned out that we are living with symbiosis with billions of microbes with us on the surface of our surface. The same is with animals, the same with humans, but as far as we are talking for the agriculture, especially for the water use, and the plants are those which are actually supply the food for the animals. Here already we know that a number of microorganisms like nitrogen fixing bacteria like Hydrolia and other mycorrhiza are dealing with the root system and supply efficiently the nitrogen plant. But here our role, like as a scientist, to see these billions of microbes, we actually deal with the efficient use of water. And here is the big picture, whether can meet the whole microbiome and to read the genome, the microbiome with the genome of the plant. And I think the opportunities are here, and by the establishment of the number of big collections of the microbiome, we have a great future to deal with drought tolerance using microbes. However, we heard that the digital agriculture is coming in place and playing more and more role like a holistic approach. How can make, for example, agriculture more or less robotized and make the farm management system extremely efficient by robots and the other possible intelligent tools. Here for the irrigation, by using the drones and the other this system, we already can enter in the soil and to recognize by even the distance 1 or 2 centimeters and to see in the different in one field whether we need and which if we need which corner of the field we need to be irrigated or to this irrigation. Simply here the resources and the tools are entering now, and they can increase the efficiency of the agriculture and the plant production very much. So only if we look at what I said so far in terms of the conventional and the organic farming, I think here we can combine much more different approaches together with minimize water pollution, water irrigation, and organic farming, because we deal with non-tilling, where we're dealing with less pesticides or more biopesticides on the microbiological base. And here I would like to mention, for example, that together with a small company, we deal with a so-called extra soil, which is 7 microbiological strains, microbiome strains, and starting from the resolving and finishing with the bacills, and we offer a system that we make the plants efficient, immunoefficient, but also the plants turn out to be more drought tolerant. So having this in combination for making all together like like a pool. Actually, we are going and we are in the full accordance with new strategy of Europe, like green Europe, and to make Europe carbon efficient. The carbon efficient is strongly related with water efficient. So what the new president von der Leyen is saying that big money resources will be directed deliver to those big gain, and this is that we have to keep in mind and utilize in order to make this water resilience and drought resilience more and more acceptable and more traditionally to deal in the future. We need environmental and social culture, but also policy and public framework and any investment. So with this, I finish my presentation. Thank you very much, and I'm open for questions.
Thank you, Professor Atanassov. I think you made a good coverage of the topic of drought from the perspective of life science, from the perspective of plants and their development. And now I would like to give the floor to our last speaker, who will approach the same topic, but more from the engineering perspective, and give us a broad global view on water reuse as probably the biggest expected solution, or one of them, of droughts. So, Josef Lahnsteiner, the floor is yours. Thank you.
Thank you, Rado. Yeah, I'm Josef Lahnsteiner. I am Director Research and Development of the WABAG Group, and I'm also Chair of the IWA, International Water Association's Specialist Group on Water Reuse. The outline first, I will give you a short introduction, then I will talk about urban and environmental reuse in Egypt and Saudi Arabia, then I will address industrial reuse and recycling in India. Last but not least, I will talk about potable water reuse, about indirect and direct potable reuse projects, and finally I will draw some conclusions. The drivers for water reuse are, first of all, water shortage, which is caused by climate change, population growth, urbanization, industrialization. Another major driver, of course, are economic reasons.
Joseph, excuse me, can you share your screen?
The screen? Oh, sorry, I thought you can see it. Just a moment, I have to... can you see my screen now?
Not yet.
Share and just a moment.
Sure.
Can you see it now?
No.
No. Just a moment. I share content. So.
Yes, it's coming.
Sorry. Now it's, and I full.
Yes.
Presentation mode. Can you still see it? Yes.
Yes. Perfect.
Okay. I was talking about the drivers. Yes, economic reasons. Used water or wastewater is a drought-proof resource. There is a boost in water supply security. Water risk is also a business risk, and in potable supply, it's also a political risk. Other major drivers are policies, regulations, and guidelines. For example, the new EU regulation on minimum requirements for water reuse, which was issued in May 20 this year. Other example for a policy is from India, from Gujarat, the reuse of treated wastewater policy. In China, there is the code for design of wastewater reclamation and reuse as an example for a regulation. And in Saudi Arabia, the irrigation water quality standards of the Royal Commission's environmental regulation from 2015. Now I come to the first two cases. It's reclaimed water from municipal effluents for urban and environmental reuse. In this photograph, you can see Madinati. It's a satellite city of Cairo. It's very modern. It's very new, modern, and green, and they need a lot of irrigation water. The reclamation plant is very simple. It's secondary treatment by activated sludge, tertiary treatment by sand filtration, disinfection by chlorine. And this slide shows on the left-hand side the nitrification tanks. Then on the right-hand side, this photo, the reclaimed water pumping station. The plant has a capacity of 2 times 40,000 cubic meters a day. The reclaimed water guarantee values, for example, are COD less than 50 milligrams per liter. Residual chlorine has to be greater than 0.5 milligrams per liter. Fecal coliforms have to be less than 2.2 per 100 milliliter. It's an Egyptian standard. Yes, the next example is in Saudi Arabia. It's a water reclamation plant under construction during the COVID crisis. The client is Marafik Power and Water Utility for Jubail and Yanbu. It's on the east coast in Saudi Arabia, on the Gulf on the Arabian Gulf. Contract value 120 million euro. The process, as in the Madinati case, secondary and tertiary treatment plus disinfection. Capacity is higher, 120,000 cubic meters a day. The irrigation, I mentioned the standards already from the Royal Commission. The standards have to be met, and the water reuse applications are irrigation of green areas, as in Madinati, but also the augmentation. It's an environmental reuse application, augmentation of these subcut wetlands. It's a very important birds sanctuary. The schedule of the project, you can see construction started in July last year. End of construction will be April of next year. Deliveries of equipment started in July this year. And the status of the project is that the progress of construction is according to the schedule I presented. In July this year, they accomplished 2 million safe man-hours without any incident. 2 million safe man-hours means 300 man-years without accident. There are 1,000 people on the construction site. They had 5 positive SARS-CoV-2 cases. 75 people were quarantined as first and second contacts. But now, currently, there haven't been any positive cases. That means no accidents and no SARS cases at the moment. It's a great achievement, and I just can congratulate the project manager and the team. You have to imagine it's in Saudi Arabia, 40 to 50 degrees in summer, and on the Gulf or on the Arabian Gulf, it's very wet. So, as mentioned, great achievement. Now I come to case 3 and 4. It's reclaimed water from municipal and industrial effluents for the reuse in various industries. In Chennai and Dahej in India. The Coimbatore water reclamation project is located in Chennai. Chennai is the capital city of Tamil Nadu, a mega city. The capacity of this water reclamation plant is 45,000 cubic meters a day. It was started up end of last year. The process is an advanced multiple barrier system, and the reclaimed water is reused in various industries. You can see Chennai on the Gulf of Bengal in southeast of India, water reclamation plant. In the western part of Chennai, there is a 60-kilometer long distribution system for the reclaimed water, and in this town, for example, the Irungatukottai area, there is automotive industry, for example, Hyundai, and also supplying industry. And it's this reuse of reclaimed water is very important, as these reservoirs are now reserved for potable water supply. Every year before the monsoon, they have a drought, and Chennai is very, very water stressed. The simplified process flow diagram, the secondary effluent comes from the Coimbatore sewage treatment plant. The core technology of the reclamation plant is ultrafiltration, reverse osmosis, and disinfection with ozone. And as mentioned, reuse is via a 60-kilometer distribution network in various industries. The major parameters for industrial reuse: total dissolved solids in the raw water 1500 design value, reclaimed water has to be less than 70. The actual values in August were less than 50. Total silica is also very important, 40 milligrams per liter in the raw water, less than 5 in the reclaimed water. Actual values in August were less than 1 milligram per liter. On the left-hand side, you can see the ultrafiltration unit. It's from the German Inge company. Right-hand side, reverse osmosis from Dow, a brackish water reverse osmosis. As mentioned, Chennai is very stressed. They applying also advanced water reclamation systems, and therefore it's the right place for the next conference, the next global conference from IWA on water reuse. It's the 13th IWA International Conference on Water Reclamation and Reuse, will be organized in January 2022 by the IWA Water Reuse Specialist Group and Federation of Indian Chambers of Commerce and Industry. It's a I'm optimistic, and it's a post-COVID conference. If you're interested in water reuse, it's the event, and I cordially would like to invite you. Now, I come to industrial recycling. In this petrochemical complex, it's purified. This is a purified terephthalic acid facility. It's from Reliance Industry, a very big group in India. PTA is a monomer for PET polymerization. PET, as you know, is used for plastic bottles, for example. And in this process, we have two biotechnology processes, biotechnological processes. It's pretreatment is by anaerobic digestion. upflow anaerobic sludge blanket, membrane bioreactor. In MBRs, the biomass is separated by a membrane, and so we can substitute big secondary clarifiers. So the core technologies, pretreatment, USB, membrane bioreactor, and reverse osmosis. The RO permeate is reused directly as as cooling tower makeup, and after polishing in ion exchange, in mixed bed ion exchangers as boiler makeup. Some parameters, for example, CUD in the raw water 6,500, after USB 1,600. After MBR, this is a target value, 30 milligrams per liter. Actually, it's 40 milligrams per liter, and in the RO permeate less than 10. Total dissolved solids, 2,900 milligrams per liter. In the RO permeate, 100 milligrams per liter, and chlorides less than 30. This photo shows the USB reactors, membrane bioreactor, aeration tanks, MBR skid and filtration cell, reverse osmosis. In this case, the membranes are from Torre. Yes, this Coyambedo plant and also this plant were operated without any disturbances since also during the COVID crisis. Its industrial water is essential, and it's considered, these plants are considered to be critical infrastructure. Now I come to potable water reuse. The major indirect potable reuse projects are the first three are the most prominent projects: Orange County, Torrelle in Belgium, Orange County in California, Singapore. New Water is very famous. The difference between indirect potable reuse and direct potable reuse is that IPR, indirect potable reuse, employs an environmental buffer as additional safety barrier. In the first two cases, the aquifer is used as environmental buffer, and in the Singapore case, they have already 5 new water plants. Reservoirs are used as environmental buffer. Worth mentioning is also the San Diego project in California. For the first phase, the construction tenders were released in August this year. Bangalore V-Valley is also indirect potable reuse project is postponed. Bangalore is extremely, as Chennai and as Delhi, extremely water stressed, and IPR is also a topic in the megacities of Delhi and Chennai. So it's discussed, and I'm sure it will be realized in the next 5 years. Now to the major direct potable reuse projects. Windhoek, Namibia, they started already more than 50 years ago in '68. In the old Korean Gap water reclamation plant, they employed until 2002 a conventional system. Conventional system means no ozone, no membranes. In 2002, the new Korean Gap water reclamation plant was commissioned, and they are employing an advanced multiple barrier system. I will show later some slides about Windhoek. The Beaufort West project in South Africa is another example for DPR. Big Spring, Texas, they started blending operation in May 2013. Wichita Falls, also in Texas, emergency operation from mid-14 to mid-15. Now then they switched to IPR. And Another example is El Paso, also in Texas. Pilot testing has been successfully completed. Now they are designing the full-scale water reclamation plant. They call this Advanced Water Purification Facility. Windhoek. This slide shows a simplified portable reuse, direct portable reuse scheme. The raw water comes from this wastewater treatment plant. It's secondary effluent, which is polished in maturation ponds and then treated in the new Gap water reclamation plant. A maximum of 21,000 cubic meters a day is directly blended in the distribution system with treated dam water and groundwater. And on an average basis, 25% of the drinking water of Windhoek is covered by reclaimed water from domestic sewage. Domestic sewage as industrial wastewater is strictly separated in order not to contaminate this domestic sewage. The reclamation plant, Norbert already showed this plant because we have a joint project with regard to antimicrobial resistance. The system consists of pre-ozonation for pre-oxidation, pre-disinfection, then particle removal by coagulation, flotation, coagulation, flocculation, dissolved air flotation, dual media filtration, then main ozonation for main oxidation of micropollutants, and also main disinfection of protozoa, bacteria, virus. With regard to COVID, we consider this plant very, very safe. The ozone cracks dissolved organic carbon, which is made bioavailable, and these biodegradable substances are polished or degraded, removed in this biologically activated carbon filter. Next step is a 2 stages activated carbon adsorption process in order to adsorb residual micropollutants, and then ultrafiltration in order to remove residual, let's say, protozoa or bacteria. Then we have chlorine disinfection and stabilization with sodium hydroxide. A comparison of reclaimed water with the treated dam water shows that the reclaimed water is superior to the dam water. For example, turbidity 0.05 NTU in the dam water, 0.6. Dissolved organic carbon 1.7 milligrams per liter in the dam water, 3.6 milligram per liter. So why is it accepted? There was no other choice due to severe water stress. They had many droughts, and there were a lack of other cost-effective options. Transport from distant sources is 5 times more expensive than direct portable reuse. Very important, since the beginning of direct portable reuse in '68, no outbreak of waterborne disease has been experienced, and no negative health effects have been attributed to the use of reclaimed water. The city of Windhoek has an excellent information policy. There is trust in the multiple barrier approach and the technology. The plant is monitored by local staff and also maintained by local staff. This increases also the trust, and I would say it's a real success story. As Norbert showed, antimicrobial resistance, even genes are removed completely. And during the crisis now, the plant was operated without any disturbances. Fortunately, there were no positive cases of the operating staff in the operating staff. Yes, now I come to the overall conclusions. Large quantities of fresh water, it's very important, can be saved by water reuse. This boosts the water supply security. The environmental impact, of course, is reduced by water reuse. Many cases, water reuse is cheaper than other options, especially if it has to be transported from distant sources. Then the undisturbed functioning of the water supply, especially during a crisis, as the current crisis, is essential. This can be guaranteed by properly designed, resilient multi-barrier processes and professional O&M. And finally, it can be concluded that water reuse represents a major factor in sustainable development. I thank you for your attention.
Thank you, Joseph, for this presentation and for this overview of technologies, specific projects, and how people perceive them. I think one of the clearest conclusions from your presentations is that water reuse and water reclamation is happening at a large scale globally, because I think all of us who are in this discussion at the moment, panelists, attendees, are situated in Central and Eastern Europe. I would be relatively surprised to know that there are people outside our region, and I believe that for us this still sounds very much as something exotic here. At large scale, I don't know of many facilities at small scale, like golf courts, certain industrial plants, etc. We all know in Eastern Europe reclamation and water reuse plants, but at a large scale, and particularly for potable water, there are not many big ones. And what I'm trying to say is that your presentation is giving us the flavor that these things are happening in various locations around the world. Of course, the big driver being the need for water, that's as simple as that, but the variety of technologies and uses is interesting. So thank you for that. Now, I think we are all ready to address some questions. Frankly speaking, I had myself prepared some questions, both because I was curious to ask you some things and also because I wanted to make sure that I have a buffer of questions, but we received quite a few more. So I wouldn't bother you with my questions. I'll start straight away giving you the questions of our attendees, more or less in the order in which they came, and I will give you like pairs of questions when there is more than one question to a specific panelist, so you can address them one after another without coming back and forth. So a set of questions to Norbert. First question is, do you proceed some genetic investigations of the tap water in Wien? Well, that's question number one, tap water specifically raised question. And the second question also to you, Norbert, it sounds like a kind of a rhetoric question, but still, is the added value of wastewater monitoring, drugs, antibiotic resisting viruses, recognized by national authorities such as healthcare, police, etc.? Please, thank you.
So thank you for the questions. To the first question in regards to the monitoring of the drinking water, the tap water of Vienna, not the final water, but there are actually the molecular methods are applied in for two questions. The one is source tracking. So when you know that the water is coming from high mountain areas, so when they have for some reason a turbidity, and they have to turn the water away so that the turbidity does not pollute the distribution net. They are investigating with molecular methods what's the reason for that turbidity. So whether this is fecal coming from wildlife, whether it's fecal coming from livestock, or it's fecal coming from humans, for example. So this is one aspect, trying to figure out where a pollution comes from. So again, so they do online measurement, and when certain trigger values are exceeded, then they just close the pipe and discharge the water. But nevertheless, they want to figure out what's the reason for that. So there's automatic sampling and analysis. Another another topic where the molecular methods are applied is in regards to understanding or optimizing biofilm, also understanding disinfection, efficiency of disinfection. They are trying to change a bit on the disinfection system, so they use those methods to evaluate the technologies and to evaluate the operating conditions of these systems, and use molecular methods too. And linked to that, basically, it's a bit of biofilm analytics. So what type of bacteria are within the biofilm, and is this a problem or is it not a problem? Because, you know, there is a shift in the how to say, in the attitude toward biofilms in drinking water. So in former times they were considered as very, very bad, and nowadays one say, well, not necessarily. So they have their certain disadvantages too, and so when it's a good biofilm, it can survive, otherwise it get killed. So this is partly done in routine and partly done in smaller research projects. But in regards to conventional, conventional monitoring of the water coming out of the tap, it's not used. So there, as there is nothing in there. The second question in regards to the whether those methods, these epidemiological approaches, or wastewater epidemiological approaches, are used or accepted by officials. Well, that was not the issue till now. You may know that there is this official European drug report, and where they assess the drug consumption in all member states. And in parallel, there is always, at the same day, there is the release of investigations on wastewater assessments for drugs that are performed in parallel, and then the numbers are compared. So this is, so it's now considered as very, how to say, reliable, but it's not an official tool that is applied, and that means that when something is not an official tool, then it's not accepted by police or some other authorities in that regard. But on the research side, it's in Austria, for example, every year different wastewater treatment plants are participating in that survey, and nowadays it's already a rather huge share. So some of them are doing the investigations every year, and others are just doing it the one or other year. So there's a bit of permutation and some stable data, or some stable sampling places, so that you can estimate certain trends around that. I hope that answered.
I think so as well. Thank you. The next set of questions are addressed to Professor Atanassov. They come from the same person, and I will just read them together. Does the EU regard gene editing techniques, actually these are not specifically water questions, but rather genetic biotechnological questions. Does the EU regard gene editing techniques where no foreign DNA is introduced into the plant genome, such as CRISPR, as genetic modification? Will it be regarded as GMO is the question. So if we can simplify it, is CRISPR GMO or not at the EU level? And related question, beyond the European Green Deal, could we expect similar initiatives to be undertaken worldwide? These are the questions.
The first one related to the GMO, I understood, but second one I did not catch what exactly, but then will tell me if it's needed. So the GMO technology, although it's an old technology for me, has been already tried to use different spectrum of multi-genes or single genes to be transferred to the core maze and width. It has been achieved and already tested for 10 years in the field, but it turned out, because of the different reasons which I cannot understand, that they have been not commercially approved and they are not commercially used. With the other words, there are good results, but they are not practically realized with the other words. So here, the question, however, is returned to the new plant breeding techniques like gene editing is another story, because now we have the options how to deal with elimination of those, for example, promoters or regulator genes or transcription factors of the multi-gene family, in order to make it the plant itself without genetic modification more tolerant to the water use efficiency. And this is in the process of development. And already the Professor Shinozaki in Japan is close to develop plants, rice, and Chinese scientists, which might be suitable for to be used with less water, and or to develop upland rice, which is without any water. And here the progress is obvious, and we are looking soon to be to be released. So here the question is, if you look at Europe, is that we're actually under pressure and the law which does not allow us to make this one. So for me, if you look at Bulgaria, for example, a number of southern countries and different regions, starting from Cyprus, Greece, Portugal, Spain, Atanas, Serbia, Bulgaria, we have to deal with alternative crops. And these are a number of crops. For example, we can have sorghum, we have topinambur, which are plants which can supply with the respective biomass or proteins needed substances for the feed and food. So I'm here optimistic because in relation with agronomical practices which are already very efficiently developed, new irrigation techniques efficiently developed, robotic sensors and precision farming already is in place. Tomorrow, I think with our mobile phones, we could be capable to control a number of factors which make the plants efficient with the water use. This is in part of the GMO and the other techniques. What is the second question?
The second question was too broadly formulated. I'll just read it and we can reflect on it, or if the person who asked it wants to make it more specific, please drop a note. The question is, beyond Europe's Green Deal, could we expect similar initiatives to be taken worldwide? I'm not sure whether it means similar initiatives like the European Green Deal or...
This looks like a common set of questions. Huh?
Yeah, I think it complements the previous question on gene editing.
I think I already make possible explanation about gene editing.
Yeah.
Here is with one well, because the technology is developing and make more and more efficient day after day. There is no limitations here. Let's put it in this way.
Yeah.
And yeah. So and here is I think we have to regret, because this looks like a mutagenesis. It's if one single nucleotide change or replace with another nucleotide with the same plant, and you cannot recognize, you cannot make the difference between those which are developed by experimental mutagenesis, classical mutagenesis, by radiation or chemical mutagenesis, with the gene editing. And then the question is, and then what? You cannot make a recognition, and you bend the development with the gene editing. So here 132 organizations, instead to make this happen in the plants, in animals, and in microbiome, and to make all these deals, because this happens every second in the nature. This is every second happen in our stomach. Every second. And this is in plants, etc., etc. So what we do to make nature more efficient and to help those biological farming, etc., more efficient, more cheap, we are actually banning those developments. So with other words, replacing the old technology with GMO gene editing is really a part of our future, and we have not to make such a unlogical, let's say, decision. Yeah.
Thank you, Professor Atanassov. Actually, we just got the clarification from the person who raised that question, and but I think it's the answer is relatively obvious. I mean, it's the question about the Green Deal for climate policy in the EU. Can we expect other big economies to take action towards climate change? I think it was yesterday when China announced that they want to be carbon neutral by 2060 or 2055 or something like that. So probably for the time being, everyone except for USA, but hopefully that will change in November, is planning things like that. So I don't know what else could be answered to this question, but if anyone from the panelists wants to address this specific one. But I would rather switch to the other more specific questions from other attendees, specifically to Joseph on water reuse. And please, if the other panelists want to say something when I am addressing a question to a specific panelist, please feel free and raise a hand or just kick in. So the question to you, Joseph, let me just read it properly. How many countries in Europe use recycled water? What percent of total countries globally use recycled water?
I'm not sure about the exact number, but in the southern countries, irrigation is a big topic. Spain, Italy, Cyprus, especially in Spain, for example, in the Murcia region, they are very advanced. They have already membrane plants for treating irrigation water. And there's also a big initiative in Lisbon for urban reuse. And even in Belgium, I presented this shortly in Toirele. There's aquifer recharge. That means it's indirect potable reuse. It's done in Belgium. In Germany, for example, of course, a high degree of industrial reuse, and so it's many countries. But yeah, and globally, the hotspots are, of course, the dry countries or the dry continents. It's Australia, California. California is meanwhile very advanced in portable reuse, but also industrial reuse. India is one of the leading countries in industrial reuse. We have an estimation they treat daily 3 million cubic meters. 3 million cubic meters for industry they produce 3 million cubic meters of reclaimed water for industry. I showed 2 examples. And Singapore is very water stressed despite a lot of rainfall. They have 4 water taps, national taps. It's water from Malaysia, but the contract is limited, so they want to become independent. So they have seawater desalination, but it's not so cheap. They have this new water production, and they have rainwater. Of course, Southern Africa is very dry, Northern Africa, Middle East, so it's many countries.
Thank you. Yeah, I think it's many countries, and more will be coming. So the direction is quite clear. Thank you for that. I've got one question myself for Teodora here in our room. It is regarding the role of water operators, water utilities, because quite a lot of her thesis was pointed towards the role and the capabilities of laboratories in water utilities. So my question is, why do you believe that it is actually the water utility that is the logical place for such analysis to take place? I mean, I believe the overall institutional setup in most European countries is relatively similar. We have hygiene-related authorities, regional health inspectorates, basin directorates, etc. So it's not a rhetorical question at all. It's a question which I would like to hear opinions on. And actually, if other panelists want to address it as well, please feel free to do so. Do you really believe that the water authorities, because of capabilities, because of capacities, because of what they need to do anyway, are the place for many of these things that currently sit nowhere? Should they take place mainly in water utilities or entirely in water utilities? Why, how, etc.? Thank you, Teddy.
Thank you for the question. Well, I would say that naturally the water operators, the utility companies are having responsibility towards the quality of the water supplied at the taps in our homes. By saying this, I will insist on the role of the utility operators because at the end of the day, if anything happens, if a neighborhood of people becomes sick due to a new virus in the water, then the responsibility goes to the utility operator. So having this said, I would add that, okay, the utility operator is having the responsibility and they should be playing a significant role, but they're not the only stakeholder. And I think there should be some kind of ecosystem between the utility operators, the health authorities, the research institutes, maybe the producers of, for example, PCR equipment when we speak about the laboratory testing of water, to come together into some kind of working composition that would allow to first go to a broader discussion of the topic, to find suitable and cost-efficient option for the water operators to start implementing PCR equipment for their daily routine analysis in the microbiological labs. And at the end of the day, the benefit of such collaboration, in my view, is for the whole society. It's not only for one stakeholder or another. So bringing together those stakeholders may be driven by the utility operators in some collaboration with the health authorities would be great. And I believe that it will give better options to the utility operators to plan also their future investments into protection of water sources, but also into new technologies for drinking water treatment or wastewater treatment before discharge. This will allow the water operators to also think in the direction of possibly new ways to disinfect the drinking water, depending on what they could expect. And here, I believe that the research institutions and stakeholders would also be very useful, because those are the places where the main part of R&D is happening today. I mean, the utility operator does not naturally do research into their laboratories, but they would be the beneficiary of such researches and allowing some kind of trial tests in smaller size before they implement like a new chemical or a new technology to provide more secure and safe future for our drinking water.
Thank you, Tony. And this is something I wanted to get as an answer, because routinely when we speak about water, we want to see a bigger role for the water utilities, so hopefully they will fill that space with competencies and natural activities. I have one more question to Joseph, and it is provoked to an extent by the presentation of Norbert, but also something that I listened to this morning. Now, my question is the following. If you take as an example some of the most advanced water reuse plants for potable water needs, let's say for direct potable water treatment that you presented, so think about an advanced plant in a country that can afford to pay high operational costs for treating water for direct potable water use. Now, I think I saw somewhere in Norbert's presentation that so many things still go undetected, and some of the things that are detected, such as critical substances, pathogens, traces of viruses, etc., are so small that even the best available technologies like reverse osmosis and probably even nanofiltration, ultrafiltration, etc., cannot guarantee that they will get treated. So long story short, my question is the following. If you take the most advanced treatment solution for direct potable water, do you believe that everything that is detectable or even undetectable is treatable now? If not now, is this a problem when we treat, etc.? Any reflection on the question? Thank you.
Yeah. What we can detect is not present in the final water, because in this windhook plant, it's a real advanced multiple barrier system with 9 or 10 treatment steps. And in any case, the standards are met, of course, from WHO or other standards. And we have comprehensive monitoring programs. And so far, we haven't detected any harmful compound in the final water. Perhaps there are unknown compounds, but this problem you have everywhere. So I just know this advanced multiple barrier system is very safe. And we remove antimicrobial resistance, also antibiotics or hormones, endocrine disruptors. These compounds are not in the final water.
Okay, so your answer is pretty positive. what is currently detectable is more or less treatable, and I believe that if it's not treatable in the kind of plants that we're describing at the moment for water reuse, it's definitely not treatable in the vast majority of conventional water treatment plants.
Yes,
anyway.
in conventional river water treatment plants, the quality is not as good as in this reclaimed water. I showed a comparison of treated dam water. This quality is much worse.
Yeah.
So, yeah. And its effect, de facto reuse from rivers. Upstream wastewater treatment plants discharge and the water is abstracted in conventional plants for potable water production. An extreme example is on the river Ganga. The Ganga is very polluted in Varanasi. They have a conventional treatment plant. There were no disease. They use a lot of chlorine, of course, but from a biological point of view, at least it was safe over many decades. But de facto reuse is a fact, and this controlled potable reuse is more safe than I would say conventional treatment.
Clear. I think that was a very, very clear answer. Although from someone who is doing this treatment plant, but
Okay.
we trust you as someone who has probably more experience than anyone else, at least I know, in the area. Thank you. I think we're already 2 hours and 15 minutes in the discussion. I'm not getting any further questions, and I would like to offer you something as a way of concluding our discussion, and I would like to give each of the 4 panelists the opportunity to express a final opinion or comment or whatever you want to say, but I want you to make it as an answer to the following question. And I'll make a reference to something that I came across some months ago. I don't remember the name of this German gentleman who was the most famous face in their fight against COVID. I think it was their chief epidemiologist or something like that, a gentleman with a dark curly hair. Just the name is, I can't get it. And something like Doppler or something. Anyway, he was asked about how unprepared we as the world are. And he was asked when the whole thing is over, the coronavirus is over, and obviously there is a huge risk of other things like that coming. I mean, jumping from animals to human, etc. And he was asked if he has a budget, not unlimited, but still a sufficiently meaningful budget. What would he do as a research or scientific project? And he gave a very clear answer, obviously, as someone who knows what he's talking about. And he said, I would be investigating camels. And because of the population of coronaviruses or other viruses in their stomachs. And that was a very clear answer. I mean, I was very positively surprised to hear that the gentleman knows where he expects no bats, no what was the name of these animals, pangolins, whatever. You see the point. My question to you is the following. I mean, all of you have an opinion about what is there in water, what should not be there, how it should be analyzed, etc., etc. So the question is, if you have a budget of whatever, 5, 10, 20 million euros plus minus, and you are in a position to structure a project in the context of what we are discussing today, what would that project be? How would you position it, etc.? With this, I would like to give all 4 of you the floor. Share your thoughts, both specifically in answering my question, but also if you want to add something else in the context of our discussion today. And I will give you the floor in the order in which you gave your presentation. So first I will give it to Teddy. Thank you.
Well, great question. I like to go first. I would say that in my view, those millions would to make the most benefit of them, because we can put them in any kind of a project, and maybe there are lots of meaningful projects. But well, I think that what would be worth doing is increase the capacity of both health authorities and utility operators to do fast tests with regards to microbiological pollutants and viruses in both drinking water and wastewater. So this is one, so provide the necessary equipment, train the staff, get prepared. But also I would put some portion of those millions into research, and maybe not into the specificity of the research or the quantity or the quality of research, because I believe that quite a lot of research is happening anyway in our world, but maybe to put some more light on the importance of those research initiatives, the findings from those initiatives, and bringing together the research institutions with the business, so that we could make a better use of the results coming from the research activities, and make the best of them for the utility operators, for example. That's my answer.
Thank you, Teddy. So it's a combination of fast test research and utilization of these tests in water utilities and businesses. Now I'll give the floor to Norbert, please.
Well, when it's 4 to 5 millions only, it makes a difference, or whether this is 4 to 5 billions. So if it's only, because this is the range of bit more than medium-sized horizon project, so it's from the amount of money, it's more or less a feasible amount. So it's not the wish to Santa Claus. So for that money, I rather would try to do only communication only to the consumers, trying to get them somehow sensitive to what is occurring and what they are contributing, just to get an idea, because the problem we have in wastewater treatment in general is the perception of people. And when the perception of people is like, well, it's working and it's no problem, then we have no power to convince politicians that they should give additional money for research and so on. So we should start at getting people aware that this is an important aspect of the society. And then when awareness is there, the politicians may be aware too, and think about the valuable things that we could contribute in that sector. So I think that's maybe for the first base to another step. Yeah, I think I would do that.
Now imagine you have the 5 billion.
Oh, the billions. Okay, so then I would say, well, actually, we're not doing too bad. So we're speaking about a lot of CECs and all the problems, and we are aware that they may cause problem. But bottom line is wastewater treatment is not doing too bad. Yeah. So when we have low-loaded wastewater treatment plants with nitrification, denitrification, they are really fine. So and a lot was reached during the last 30, 40 years. So we are not on a bad track. And I think we could allow to continue like that for another 10 years, just to do things that we know and that really prove to be successful, so that we have really everywhere in Europe or that planet at least this base. And within that time frame of 10 years, I would use that money to just blow up the minds of engineers and take their brains and put together a completely new approach where resource recovery is the core. So we have a lot of technologies from all over the place. And right now I have the feeling that this is rather a treatment training, one technology following the other. So this is maybe not the most efficient and sustainable way. So we really have to think about what is the advantage, disadvantage, how to recover this and that, and convert in the brains of engineers wastewater treatment plants to resource recovery plants. And the side benefit effect of that would be that we clean our water by that, because we want to take out resources, and as a side effect, we have clean water. But that requires a complete new thinking, and not continuing a path that was obviously successful over the decades, but maybe not a suitable approach for the next 40 years.
Oh, that I see what you say, and I believe and hope that some of these new mega cities that are being built on a green field, this is the place where that mindset can be changed, because when you have a legacy system and you keep upgrading that, you cannot switch to something completely new. But
No, the collections, you can keep the collection system. I'm not thinking about urine separation and so on. So this is something completely different, and this is not feasible on a huge scale. So really, you have the inflow of the treatment plant, and you have there the phosphorus. It's starting with the phosphorus actually, to recover the phosphorus. But you have a lot of other valuable substances there, and the Japanese, they recovered gold from wastewater. Yeah, so it does not pay, but it's just an idea what is possible. Yeah, and I think that requires new approaches, new technologies, new thinking to recover whatever is there. And of course, it has to do with entropy and so on. But yeah.
I'm curious what the Japanese are eating, but that's Thank you, Norbert. I mean, that's you give a scientist 5 million and he asks for 5 billion, so that's thank you, really. Now is the time for Professor Atanassov. What kind of project would you structure with a meaningful impact on society? And you may not limit your answer to water only, please.
The question was what approaches I should designate to the society?
Yeah, if you have a meaningful budget and if you can link it to water and biotechnologies.
That's a good question. So it should be, again, as I said already, the holistic approach. So what one not should only limit to the improvement of the plants, but for example, the new agricultural, for example, agrotechnology should be applied. For example, I already started to say non-tillage. It's already part of saving of the water and making the soil fertility much better. That's me make the microbiome more efficient with the plant development. So this is a number of techniques that should be applied. And the irrigation technology, generally speaking, there are a number of options to be applied. And so we know that the drill technology, drop irrigation is one of the most efficient. And here, Israel is, for example, one of the leading countries in the world to be used like an example for a model for the rest of the world, especially for Bulgaria, because as you know, rather even in Bulgaria, we have a region that the precipitation is not more than 200-250 mils per year. And this makes us a severe question what and how to deal. But then is the coming, for example, together with the precision, with the digital agriculture that can observe from a number of techniques how do we deal with water efficiency, where to irrigate, when to irrigate, how to irrigate. That is, the new technology, let's say the machine learning, robotization are here which to make us really more clever. And in the end, it is not the most, but the least is the alternative crops. So we have to look at outside to Bulgaria, for example. There are a number of like this. I mentioned one of those is sorghum. like alternative for the corn and the corn. But topinambur like alternative for the proteins in the sunflower. But we have to look at outside. There are a number of other crops in Africa, in China. For example, teff. Teff is a crop which is dealing with much less water, but is producing high efficiently grain crop with a high protein and good quality. So all this, gene banks that already all over the world with a 16 million store from starting from Colorado, finishing with the Tsukuba gene center, gene banks. We have to, to make links and start to make our own gene bank. The same not only with the field crop, but the same with, for example, with essential oil crops, with fruit crops, especially vegetables, we need much water. So the alternative crops are there, and saffron, for example, coming from Iran. It turned out that this second country which the saffron is very well disposed to be cultivated is Bulgaria. It's 10,000 people already are looking after it, and one by one it's coming. But water, for example, is you like a man which is engaged with this, and the man which I'm dealing with agriculture. We have to offer a specific strategy for the water development strategy, for example, for Bulgaria. The problems are already here, and we have to start from now to see and to look how 10 years from now or 5 years from now we can do efficiently every crop. That's a way to go.
Thank you, Professor Atanassov. So your answer is more in the direction of soil and matching the right crops with the right soil and climatic conditions. So you are making this link between water issues and the applicability of specific crops. And one specific answer which I hear in your response was gene banks, etc. Thank you for that. And now, last but not least, Joseph, what would you prioritize?
I would conduct a water reuse project in a developing country. I would build a full-scale plant and do capacity building, knowledge transfer to these developing countries. 4 to 5 million, you can build a small full-scale plant and demonstrate water reclamation and reuse. Yeah.
Thank you. Thank you. I think it was quite indicative that more or less in all the 4 answers, there was a heavy aspect on awareness and communication and capacity building. Even those of you who did not deliberately say that, I think it was there. So obviously a topic that needs to be elaborated upon and further awareness to be made, not only among sector professionals who are working in the topics of water and biotechnology, but much more widely around societies and consumers, etc. Thank you very much. I think that was it for today, at least. We got a relatively small number of attendees, but I think this did not affect at all hopefully the quality and the pace of our discussion. As I said in the beginning, this is the first time that the organizers of the Biotech Atelier recognized the topic of water and biotechnologies, and I hope that we managed to, over the last 2.5 hours, to outline certain relevant topics without claiming that these are the most important, but clearly some of the very relevant topics. I believe and I hope that this would be first out of a number of such events, both within the Biotech Atelier and probably also in other forums. So once again, thank you to Teodora, Josef, Norbert, and Atanas, and to the people who joined us today. I believe these were meaningful 2.5 hours, and thanks. Let us stop it here on a Friday afternoon, just before the weekend. Thank you all.
Thank you for the excellent moderation.
Bye-bye.
Bye-bye.
Bye.
Cheers.